Hey everyone, welcome to my CDC presentation. My name is Runhan. I'm from Nonlinear Controls and Robotics Lab of the University of Florida, and the title of my talk is Relay Explorer Approach for Multi-Agent Exploration of an Unknown Environment with Intermittent Communication. First of all, I would like to talk about the motivation of the problem. For example, if you have one or multiple underwater unmanned vehicles, then they need to acquire GPS information. The agents will have to come up to the water surface to acquire GPS, and this is time-consuming, and also at the same time, you expose yourself to the adversaries. Then, what if you can stay submerged underwater indefinitely without surfacing, but can also acquire GPS or state information from another agent? This other agent, what we call a relay agent, acts like a ferry, which will provide state estimate information to the exploring agents. In this case, the UUV can stay submerged at all times, and we call this method a relay explorer approach. In this paper, the contributions include a relay explorer control method is developed to allow a relay agent to provide state estimates to the exploring agents, and the exploring agents don't have access to the true state information at all times. Also, we developed a distributed formation and leader tracking controller, which enables the exploring follower agents to maintain a formation with respect to the explorer leader in this unknown environment using a graph theory. Specifically, I will explain the relay explorer approach in our control objective. The objective is to enable the network of explorer agents to explore an unknown environment where navigational feedback is unavailable. The explorer agents follow the explorer leader, which is following a desired trajectory through the unknown environment. The explorer leader is intermittently receiving state estimate information from the relay agent, and the relay agent is intermittently receiving the true state information from regions where feedback is available, and then communicating with the explorer leader to provide state estimate when they are sufficiently close. Once the explorer leader receives state estimate from the relay agent, and the other follower agent's state estimates are updated by the explorer leader using a distributed controller where a graph is connected at all times. As you can see in this animation, this relay agent is switching in between the feedback available and feedback unavailable region and providing state estimate to the explorer leader, and the explorer followers maintain a fixed formation in this unknown environment. For the dynamics we used to model our system, we consider a model with one relay agent and n+1 explorer agents. And for the relay agent, we use this control affine nonlinear dynamic system, where FR denotes the drift dynamics, VR denotes the control input, DR denotes the disturbance. Similar for our explorer agents, where 0 here denotes our explorer leader, and FE denotes the drift dynamics, and XI denotes the true state, and VI denotes the control input, and DI denotes the disturbance acting on the system. To achieve the control objective, we will have to make some assumptions. The undirected graph G is connected for all time, and this assumption will allow the explorer followers to communicate with each other at all times. The exogenous disturbances that we talked about earlier on the relay and explorer agents are bounded by some known positive constants. The drift dynamics of the relay agent and the explorer agent are known, locally Lipschitz, and bounded because we have to use this to facilitate our subsequent stability analysis. The relay agent and explorer leader can communicate when their relative distance is sufficiently close, so that the relay agent can communicate with the explorer leader to provide state estimates. And there are multiple known and stationary feedback regions, so that the relay agent can switch in and out to compensate for its state estimates. Then the relay agent is initializing the feedback region, and the explorer agents may be initialized outside of all the feedback regions, so that this relay explorer approach can allow those explorer agents stay in this unknown environment at all times. And the control and estimated position of the explorer leader are bounded. The desired states and their time derivatives are bounded. To compensate for this feedback intermittency of the problem, we define VR and VE as the constant switching signals for relay agent and explorer agent respectively, where TLA denotes the out time instant when feedback is available, and TLU denotes the out time instant when feedback is unavailable, where delta TLA and delta TLU denotes the corresponding dwell time conditions. Same thing for phi E. To quantify our control objective, we define three error systems for our relay agent: ER, ER hat, and ER tilde, which denotes the trajectory tracking error, the estimated trajectory tracking error, and state estimation error, where XR denotes our true state, XRD denotes our desired state, and XR hat denotes our estimated state. Note that ER is equal to ER hat plus ER tilde, and we will use this relationship in our stability analysis. And when feedback is unavailable, we are using this observer to approximate XR dot. For the explorer leader, we also define three error systems: E0, E0 hat, and E0 tilde, where X0, X0D, and X0 hat denotes the true state, the desired state, and the state estimate of our explorer leader. And note that E0 is equal to E0 hat plus E0 tilde, and this relationship will be used in the stability analysis section. And when feedback is unavailable, we have to use observer to approximate Xi dot. And similar for the explorer leader, we will have to use X0 hat dot to approximate X0 dot. Then, to compensate for the leader tracking and formation control objective, we have to define this auxiliary estimate EI hat to approximate the error of agent I. And this DI variable denotes the desired relative position between the explorer leader and agent I. Note that agent I will know this PI in unknown environment, and this variable will be used in the subsequent defined auxiliary controller design. Now we're ready to design our controller. When feedback is available for our relay agent, we're using the true state information because the relay agent will have access to feedback. And when feedback is unavailable, we will use state estimate instead of true state. And substituting in the corresponding control inputs into the open loop error system, we will obtain these closed loop error systems. Similar for the explorer agents, we design our control inputs using the state estimates instead of true states, because even though the relay agent is communicating with the explorer leader won't have access to the true state information. Therefore, the closed loop error system can be obtained as this. To compensate for the formation control and leader tracking objective, we design our distributed controller for the explorer follower I as this, where Xi hat and Xj hat are the estimated states, and the Pi and Pj denotes the desired relative position vector of follower I and its neighbor J with respect to the explorer leader. Then the closed loop error system can be obtained as this. We define capital E hat as the stack form of the estimate error of agent I. Then we take the time derivative of capital E hat and obtain E hat dot. And all these signals can be upper bounded. The details can be found in the paper. For the state estimation errors, we will use ER tilde dot and E0 tilde dot to represent the time derivative of the state estimation errors for the relay agent and explorer leader respectively. And the ER tilde dot and E0 tilde dot will be used in the subsequent stability analysis to find the corresponding dwell time conditions. And here comes to our mean results. We will have 6 theorems. Theorem 1 proves the stability of the trajectory tracking error of relay agent when feedback is available. Theorem 2 proves the stability of the estimated trajectory tracking error of relay agent when feedback is unavailable. Theorem 3 proves the stability of the state estimation error of relay agent when feedback is unavailable by satisfying this dwell time condition. Combining theorems 2 and 3, we can show that the stability of ER when feedback is unavailable by using the relationship of ER is equal to ER hat plus ER tilde. Theorem 4 proves the stability of the estimated trajectory checking error of our Explorer leader when feedback is available and when feedback is unavailable. Theorem 5 proves the stability of the state estimation error of Explorer leader when feedback is unavailable by satisfying the maximum dwell time condition. And Theorem 6 proves the Explorer agents achieve formation control and leader tracking with the distributed controller, and this will allow the Explorer followers to maintain a fixed formation in this unknown environment. To prove the theorems that we mentioned in the previous slide, we defined some positive constants. Based on Theorem 2, we defined E hat capital MR and E capital MR. These two constants are used in Theorem 3 to determine the maximum dwell time of the Rayleigh agent. And based on Theorem 3, we define E tilde capital MR. And this value dictates how large the state estimation error of the Rayleigh agent can grow before it has to go back to one of the feedback available regions to compensate for its state estimate. And based on Theorem 4, we define E hat capital ME. This value dictates how large the estimated trajectory checking error of the Explorer leader can grow before the Explorer leader has to communicate with the Rayleigh agent. And based on Theorem 5, we have to define E tilde lowercase me and E tilde capital ME, and we'll have to select E tilde capital ME to be greater than E tilde capital MR. And this inequality will allow the Rayleigh agent provide a better state estimate to the Explorer leader. And at last, we have to select E tilde capital MR and E tilde capital ME to be smaller or equal to the communication radius of the Rayleigh agent. To summarize my talk, this paper's contributions include a network system with one Rayleigh agent and multiple Explorer agents to allow the explorers to navigate the unknown environment indefinitely. The Rayleigh agent only needs to communicate with one Explorer leader to provide state estimate, and the distributed formation and leader tracking controller is developed using state estimates to maintain the multi-agent system formation in this unknown environment. Future research includes considering the drift dynamics for the Rayleigh and Explorer agents are unknown, and use a multiple timescale deep neural network learning architecture to approximate this unknown drift dynamics. In addition, we'll focus on using a time-varying graph topology with optimal path planning for the Rayleigh agent, so that the Rayleigh agent can switch between feedback available and unavailable regions, and also communicate with the Explorer leader more efficiently. Thank you for listening. Please let me know if you have any questions.